Okay, so we know that a magnetic field is produced around a wire that has a current flowing through it that's connected to a battery. So we can find out the direction of the magnetic field using a couple of tricks. So the direction of a magnetic field at a point is defined as the direction of the force on a north pole of a magnet placed at that point. So basically, what would a north pole of a magnet do at that point? So these couple of tricks are called the left-hand rules. So if you've got a straight wire with current going through it, all you do is you hold up your left hand in the shape that it shows you there, and your fingers, if you point your thumb in the direction of current flow, so in this case, remember current goes from negative to positive, so current flow is that direction. So the left hand thumb is pointing in that direction, and you sort of coil your fingers a little bit, and those fingers point in the direction that the magnetic field would be. So you can see here, the direction is that direction, so like that. Okay. And also, you can use a different left-hand rule for the magnetic field around a coil. So if you coiled up a wire, it's different. Okay, so it doesn't form a loop anymore. The shape of a magnetic field around a coil is similar to that around a bar magnet. And those of you that did the magnetic fields with me will know I call it sort of burger shape because you've got your burger buns and your lettuce sticking out the edge. So in this left-hand rule, which is completely different to the other one, your fingers now point in the direction of the electron flow. So your fingers now, you're in the same kind of shape, but your fingers are coiling round, and that's the direction that the electrons would flow in. So negative to positive. So your electrons are flowing like that. And therefore your thumb points towards the north pole of our magnetic field. So this would be your north pole, and that would be your south pole. Luckily, you don't really need to do anything with these left-hand rules. It's just for information. Okay, the next page is another experiment that I'm going to link you to the video straight afterwards, but I'll just go through it first of all. So what this one is basically making an electromagnet. It might be that you have the equipment at home to do this, but it might be that you don't, so that's why I'm going to link you to a video of it. So what we have is a low voltage power pack, so a couple of batteries, and a wooden pencil. We also have a brass rod, and we also have an iron nail, I think, in this electromagnetics kit. And we also have wire. So we take quite a bit of wire, about 1.5 or 1.25 meters of wire, and leave a little bit of each end. So it's sort of, and then we're going to coil around the wooden pencil. So basically, what it would look like is you'd have wire, then it would be coiled around the wooden pencil, and then a bit of the wire left at the outside, because these bits of wire get connected to your battery box there. Okay, so this wire is one big wire, but this bit is coiled and then it gets connected to the battery. So we start off coiling it around a wooden pencil, which gives you a wooden core. It means there's a wooden bit in the middle here. So this is your core here in the middle of that coil. Okay, and then once it's connected to a battery pack, you can basically check whether there's a magnetic field by seeing if it pick up any paper clips. Okay. So then you switch off the current and you slide out the wooden pencil, and you'll see in the experiment that I show you that doesn't work. The pencil doesn't work. So then you replace that pencil with a brass rod, and you do the same. See if it picks up any paper clips. And you'll see again in the video it doesn't work. And then you replace it with a steel rod. Okay. And then you find that the steel rod does work. The steel rod inside a coil of wire connected to a battery does pick up paper clips. And take the steel rod out and you try it with an air core, so that means there's nothing inside of it, and again, it doesn't work. So the observations from this experiment are as follows. If we put a soft iron core, so that's steel, inside the solenoid, and that's your coil of wire, the strength of the magnetic field is increased. When a magnetic material is placed in a magnetic field, it turns into a magnet. An electromagnet is formed. So anything steel, if you put it inside a coil of wire, inside a magnetic field, it starts acting like a magnet. So material which is not magnetic, such as wood or brass, cannot be turned into a magnet. And a soft iron core should be used to make a good electromagnet, which produces a strong magnetic field when a current flows through its wires, but does not stay magnetized when the current is switched off. So basically, you can switch this magnet on or off again. So when the electricity is on, it acts like a magnet. When it's off, it doesn't act like a magnet. Where could this be used? So I'd like you to have a think about that and post in the teams what you think you could use it for. So and you can reply to each other. You can post in the main channel. I don't mind other people that can get it. So it could be used something that would be useful that's magnetic, and then you can move it so it's connected to it, picks up something magnetic, and you can move it somewhere else and then stop it being magnetic anymore and drop it maybe. Just at the bottom it says, if you wanted to make a permanent magnet, you'd use a different material, a hard steel material. But that means when you switch off the current, it's still a magnet, so it wouldn't really be, you couldn't turn it on and off again. So we'll talk about that in teams later. You can watch the video of the experiment